So good evening, everyone. My name is Abhishek. I welcome you all to the week 10 live interactive session on the NPTEL course Applied Thermodynamics for Engineers. Previous to this, we have already covered a vast process of this course where we have discussed basic thermodynamics, the pure substance, even the gases. We have also discussed about the PVT relationship for the gases. And after that, we have applied this basic thermodynamics to understand air standard cycles, Brayton cycles, also Rankine cycle. And lastly, we have also covered the refrigeration cycles as well. Now, in this particular week, we have covered, we'll be covering the gas mixtures and how to calculate its PVT relationships and what are the two basic laws that will be governed, that will govern the mixtures. Okay. So prior to that, if you have any doubts or something to ask, you can kindly write a mail on this mail ID and I will try to answer to you as soon as possible. And if you are missing your lectures, then the recorded version of this lecture will find in this NPTEL channel. Okay. Now let's move ahead. So in this week, we covered lecture number 26 and 27, where we were vastly talking about the mixture of gases. Mixture of gases. Now, these gases can be real and can be ideal and real or real. So based on that, we have you might have remembered that the instructor has solved a lot of questions to explain you how the consideration of real gases changes the value that were calculated assuming ideal gases changes vastly. Okay. So prior to that, the two basic laws that that is covered in this lecture number 26 is one is Dalton's law of additive pressure and is Amagat's laws of additive volume. Now, what does it say? The statement is such that it states that the total pressure exerted in a mixture. So, what are the keywords that you need to notice is exerted by a mixture of non-reacting ideal gases is equal to the sum of the partial pressure of the individual gases. Okay. Now, the other term other expression can be like each gas in the mixture behaves independently and exerts the same pressure as if it were alone in the container at the same time. Now, to make it more simplifier, what does it say is, for example, there is a container. There is a container. This side is A and this side is B, and there is some gas here, gas 1 and gas 2. And this is now separated by a membrane. Okay. Now, after this, let us say this will be having certain pressure PA and this will be having certain pressure PB. Now, once this membrane is removed, now both these gases will mix, but the one thing is that it is a non-reacting gases. So there won't be any formation of a third gas or a third type of gas. So this gas won't be reacting. So you will find both of this gas 1 and gas 2 in this mixture also in this mixture also. So it will be like gas 1 and gas 2, both will be there. But what will be the pressure inside this container that can be defined by the partial, there's a summation of partial pressures. Partial pressure of these two gas. Now, how do we find out the partial pressures for partial pressure? It will be based on the ratio of the molar fraction or the mass fraction or the mass fraction or the volume fraction is multiplied with the total pressure. For example, the final pressure is PM. So let us say the gas 1 has n1 number of moles, and when it is taken in ratio with the total number of, this is Nm is the number of moles of the mixture into Pm. This gives the partial pressure of gas 1. Okay. Now, this one plus the other gases partial pressure will be equal to will be equal to the total pressure, that is PM. Okay. So this is what does it say. And the other way can be thought about is that after this mixture, once this mixture has been formed, and for example, now we want to separate, we want to put them into the same container, but separate, we want to separate it. Then if for example, gas 2 we remove and gas 1 is in the same container of the volume, then it would exert the same pressure, PM into its mole fraction. Okay. This is the pressure that it would exert. And the same goes for the second gas as well. Okay. So that is the main, that is the simplified meaning of the Dalton's law of additive pressures. Now, the second law that we covered was Amagat's law of additive volumes. What does it say? Amagat laws of additive volume says that the total volume of a mixture of the ideal gas is equal to the sum of the partial volume that each individual gas would occupy if it were alone at the same temperature and the pressure as the mixture. Okay. So this is the thing that you need to notice, that it should be at when the mixture, just I will explain you. For example, this is a mixture of two gases and the pressure is PM, temperature is TM. And let us say there is some amount of gas 1 and gas 2. Now, for example, this same volume, within this same volume, the temperature and pressure is same. If only gas 1 is there, then also it would exert, then also it will acquire the same volume. Okay. And that and how can it be connected? States that the total volume is equal to the sum of the partial volume that each individual gas should occupy. Okay. Now, if the both are separated, now this and we want to keep it at same pressure and temperature, then this gas 1 would acquire a volume of its mole fraction into Vm. Okay. That is what is the meaning of this Amagat's law of additive volumes. Now, apart from that, what are the things that were discussed? That these two laws are also valid for the real gas as well, but there will be some inaccuracies, and for that we need to find out compressibility factor. Now, how to find out compressibility factor? It can be calculated by using this same compressibility factor will be proportional to the compressibility factor of this mixture can be calculated by summation of yi I is equal to 1 to k and z. Okay, that means all the gases compressibility factor you have to find out, and at that pressure and temperature, and after that you have to add them, and then you get the compressibility factor of the mixture. Okay. And apart from that, we also discussed what are the changes of various properties such as enthalpy, entropy, internal energy before and after the mixing takes place, after mixing, post mixture. How do they change? We also saw that, and we'll be trying to solve two numericals on this as well for your better understanding. Okay. So these were all discussed in lecture number 26 and 27, and I hope you can go through the lectures again so that your basics will be further clear. Okay. So let's go to solve the questions. The first question is the concept of partial volume is given by. The concept of partial volume is given by. Very simple question we just now discussed. Please tell me the answer. Okay, I'm giving you 1 minute to think about it. Just recall the question. So recall the summary that we covered just 2 minutes back. Okay. So the correct answer is Amagat's law, because Dalton's law is for the partial pressure. And Amagat's law is the partial volume. Did someone join? I would request you to just mute your mic. Thanks. Okay. And the other laws gives rule. It's generally for the phase gives phase rule is there. That is different. And K's rule is for mixture of real gases. Okay. So the correct answer is Avogadro's law. Okay. Now coming to the next question. In a mixture comprising of two ideal gases A and B, the mole fraction of A is twice that of B. Among the following properties, which one will always be equal for both the gases within the mixture? Tell me.
The temperature, sir. Temperature of the substance.
Yeah, so the correct answer is temperature because as I already said that whenever there will be a mixture of two gases, and we can find out what is the partial pressure because the amount of gases that a container has, based on that only it will exert pressure. And that, how is that connected? That is connected through the mole fraction. So for example, as this is said that the mole fraction of A is twice that of mole fraction of B. So mole fraction of the B. Okay, so that means the pressure exerted by A on the container will be twice that of B. And even the same goes for the volume, and both of these are derived from the Avogadro's laws and the Dalton's law. Okay. So mass fraction is anyways related to the moles. So this cannot be the right answer. The correct answer is temperature. Temperature will be same for if the gases are in a mixture, and if they are separated for individual gases, the temperature stays the same. Now coming to question number 3, two ideal gases have a molecular weight of, sorry about this typing errors. So having molecular weights of M1 and M2 respectively are mixed in an equal molar proportion to form a mixture. Then the apparent molecular weight of the mixture is, yeah, very simple question. It says that there are two gases which has the gas 1 has a molecular mass of M1 and gas 2 has a molecular mass of M2. So when these two are mixed, what is it? What is the molecular weight of the mixture?
It's the arithmetic mean of M1 and M2.
Yeah, so mostly whenever there is a mixture and those are mixed in the molar proportions or even mass proportion, can directly multiply as it is mixed in mixed in the molar proportions. So N1 is the gas mixture 1. So N1 into M1 plus N2 into M2 by summation of the total moles. So it is saying that both are having equal molar proportion. That means so N1 is equal to N2. Okay. So this can be taken as, if you take N1 common, and N1 plus N2 is equal to M1 plus M2, and thus it can be N1 by N1 plus M2 is equal to 0.5 M1 plus M2. So this is the arithmetic mean of M1 and M2. Okay. Coming to question number 4, in a mixture of real gases, the characteristics gas constant for each individual component is what? Does it depend on partial pressure? Does it depends on the pressure and the temperature of the mixture? Does it depend on the partial volume, or is it constant?
It depends on the pressure and temperature of the mixture, sir.
Is it? Are you sure? Characteristic gas constant it is saying.
Or equal to Cp minus Cp.
So generally it is
Constant, sir.
Yeah, it's constant. Yeah. So it is constant. The correct answer is constant. Okay. It doesn't, it is independent of the partial pressure, volume, or even temperature. Okay. It only depends on its molecular mass. Okay. Because it is telling about characteristics gas constant. Now, next question, question number 5. A room of 60 meter cube volume maintained at 300 Kelvin and 100 kilopascal is completely occupied by air, which involves 21% oxygen by volume. If air can be viewed as a mixture of ideal gases, then the specific volume of the gas available within the room air is. Try to solve this question. I'm giving you 2 minutes.
Specific volume value is around 0.78 meter cube per kg, sir. I have used that PV equal to 0.78 meter cube per kg.
Okay. So let's start solving. I think you missed a trick here. Where did you did the mistake? We'll see here. Okay. So the thing is, first read the question carefully. A room of 60 meter cube volume. So the total volume of the room is, so first of all, the volume of the room we need to find out. It is 60 meter cube. Maintained at what is the temperature? T is equal to 300 Kelvin. And pressure is 100 kilopascal. Is completely occupied by air. So the air that is there inside this room is at 100 kilopascal, 300 Kelvin, and it occupies a volume of 60 meter cube. But we say that this air is a mixture of oxygen and a certain amount of gas. Let us say that is nitrogen. So this is 21%, and minded it is by volume. And this is the other, I think 79% by volume. Okay. So first of all, just tell me what if, for example, we want to just concentrate now on the oxygen, and also the next thing that it says is if the air can be viewed as a mixture of ideal gases, So so we don't have to calculate the Z, that is the compressibility factor. So that the problem is gone from this. Then the specific volume of the oxygen available within the room air, and the other keyword is the room air. Now you tell me, if we just concentrate on the oxygen, what will be the pressure that oxygen, if just oxygen is there, then what will be the pressure that oxygen will be at? Tell me.
0.21 times of 100 kilopascal, sir.
5.21 times of.
It has only 21% of oxygen by volume.
No, no. No, it is we can, okay, that is also one of the way we can go through that. But for this question, let's start with find out what is the total number of moles, total number of moles of air in the total number of moles of air in the room, because that is the case where we know all the things. So number of moles of air is 100 kilopascal, volume is 16 meter cube, N of air into R. R is 8.314. So I'm not writing the units. I hope you know all the units. And then it is 300 Kelvin. Now find out what is the mole of air here. Calculate.
2.406.
Yeah, it is 2.406. So that is the total number of moles of air is 2.4. It is will come in kilomole. 2.4055. Okay, 2.4055 number of moles of air is coming. Now we have to, for finding out the volume of for the specific volume of the air, we need to find out what is the volume that the air oxygen is occupying. So that is 21% of the total volume. That is 0.21 into 60. How much is it? It's 12.6 meter cube. Okay, just now we have to find out what is the moles of, what is the mass of oxygen in that room. That is what we have to find out. So from here we can find out what is the, we have this is the total number of moles of air. Now out of this we can calculate what is the moles of oxygen is there. Sorry, yeah, from this we can calculate, because the volume fraction, we also know that Vi by Vm is equal to Ni by Nm is equal to Mi by Nm. This we know. Okay, so we can just multiply 0.21 into 2.4055. Calculate how much is
0.505.
yeah, 0.505 moles of oxygen is there in this room. And of course, you could have directly calculated that you were saying that oxygen's pressure is directly, you could have taken 0.21 into 100. That is true. You could have taken. I just wanted to show how the thing is coming from the total number of moles of air. But the correct approach can be the other way around also. From there, you can directly get what is the mole of oxygen. Okay, and you will get the same answer. So once that is done, what is the mass of oxygen then? Just multiply into 32. We'll get 16.16. It's kg. Okay. And sorry, it is kilomoles. Yeah. Okay. 16.16 kg. Now, the thing that you have missed here is it is asking the room air. So how much is the volume, total volume? It is 60. Okay. So you don't have to divide like don't have to divide 12.6 by 16.16. You have to divide specific volume of oxygen in the room air, because the total volume by the room occupied by the room air is 60. So 60 by 16.16. How much is this? 3.71. Okay. Did you understand? Where did you do the mistake? I know that 0.78 you would have got from 12.6 divided by 16.16. I think mostly you will get 2.6 divided by 16.16. Yeah, you are getting 0.78 here. So this is not the right way because it is asking, this is a mixture, okay? So, and that mixture is occupying a total volume of a 60 meter cube. So from that 60, you have to divide 16.16. You just have to find out what is the mass of air in that room. Okay. Did you understand?
Yes, sir. Understand, sir. Thank you.
Now question number 6. If air is assumed to be a mixture of two ideal gases, namely nitrogen and oxygen, in a volume ratio of 4:1, then the apparent molecular weight of air is. This is very simple question. I'm again giving you 2 minutes. Calculate it. Then we'll discuss.
I have obtained 27.8 kilogram per kilomole.
Okay, we'll see. 1 more minute. After that, we'll discuss. Okay, so we'll solve. This is just we have already solved one multiple choice question on this, and even we have discussed also. If air is assumed to be a mixture of two ideal gases, first of all, the key word that you have to look for is the ideal gases. Okay, that is nitrogen and oxygen. Okay, and they have a volume ratio of 4:1. So this is 4, this is 1. So what is the, if you then how do you calculate its molecular weight? First of all, you have to calculate its volume fraction. How do you calculate its volume fraction? Or even what you can do is from volume fraction, you can go for the molar fraction. So first of all, how do you calculate volume fraction? So this is just like a mixture where 4 parts is nitrogen. What is the total part of the mixture? It is 5. Then comes the volume fraction of oxygen. It is 1/5. So this is 0.8. This is 0.2. Now, as this same can be equated to the molar fraction, then how to calculate the molecular weight now? Is 0.8. So what is molecular weight of nitrogen? 28 plus 0.2 into 32 oxygen. How much is this? I'm getting 28.8 kg per kilomole. Okay, you got 27, right? Did you get
Yes,
where,
sir.
where
Yes, sir.
did
Now
you do the mistake?
yes, sir.
How did you, where did you do the mistake?
Sir, I separately calculated 0.8 into 28, it is around 20.4, and then 0.2 into 32, it's around 7.4. I just simply summed, so some typo, some errors. Sir. That's all.
Okay. Okay. No problem. Okay. So I hope you understood this question. Now we'll move to the next question. A mixture of 60% nitrogen, 30% argon, 10% oxygen on a mass basis. This is the other thing, other keyword. Mass basis is inside a cylinder at 250 kilopascal and 310 Kelvin. Okay. Now, if each of these component can be viewed as ideal gases, then the total volume of the cylinder is, and the total volume of the cylinder is 0.5 meter cube. Then the mole fraction of oxygen in the mixture is. Very tricky question. Try to solve this question. I'm giving you 3 minutes for this.
Sir, what about the argon molecular weight, sir? Shall I take it as 40, sir? 40.
Yes, 40, 40. Yeah.
Mole fraction of oxygen, I am getting around 0.072, sir. 0.072. So decimal place 1 in the sense 0.1.
Okay. We'll see. Just check your calculation. I think it is almost right, but I think you have done some mistake during your calculations. If it was correct to 2 decimals, then I think it's wrong because the answer is right that 0.1. But if it was 2 decimal, then it was wrong. It is a wrong answer. Okay, we'll discuss first. Tell me what was your approach? How did you calculate?
Yes, sir. Now, it is a combination of nitrogen, argon, and oxygen. First of all, I tried to find the mass of the mixture. So I have used PV equal to MRT. So here pressure we are having it, volume, temperature we are having it. PV equal to M. Now for finding R of the mixture, I have generally R equal to R universal divided by molecular weight of the mixture. Now the proportion is given 60% nitrogen, 30% argon, 10% oxygen. I have calculated a gas constant R, that is around 259.8 joule per kilogram Kelvin I have obtained, followed by I calculated the mass of the mixture, that is around 1.6 kg. So now after finding the mass of the mixture, I have calculated the mass of oxygen, mass of nitrogen, mass of argon individually, and followed by number of moles of oxygen, nitrogen, argon I have calculated, and then I have summed the total number of moles in the mixture, followed by mole fraction of oxygen, which is equal to number of moles of oxygen divided by total number of moles in the mixture.
What is the total number of moles you got?
The total number of moles 0.0499 I have obtained, sir. Total number of moles.
We'll see.
Let us
Although
check.
yeah, I understood your approach. Your approach is a bit lengthy, but I think you have done some mistake in calculation.
Yes, let us check it
Approach
out.
is correct, I think. So let's start. First of all, the best thing that in this question has given is the mass basis. If it was a volume basis, then this question would have been lengthy. So if it is as it has given mass basis, consider the mixture has a mixture mass is 1 kg. If mixture mass is 1 kg, then nitrogen mass is 0.6 kg. Uh, 0.3 kg is argon. 0.1 kg is oxygen. Okay. Now, once that is done, calculate its moles. How do you calculate the moles? Moles of nitrogen.
Mass by molecular weight.
Yes, 0.6528. Moles of zero point one five 32. Moles of argon is 0.3 by 40. 0.6 divided by 28. 0.02. 0.021 moles, kilomoles, whatever you, how do you represent it's fine. 32. Mostly it's kilomoles only because you are taking in kg. 0.00325. 0.3 divided by 40 is 0.0075. 0.0075. So these are the kilomoles. Now, the next thing that you have to do is summation of total moles is how much? Total moles, I'm getting 0.031. 0.031625 kilomole. Now, once you get the total kilomoles, it is asking mole fraction of oxygen. So inverse into 0.003125. I'm getting 0.098. 0.098. Okay. Which as you have to write in one decimal, it is 0.1. Similarly, find out for N2 0.021 divided by 0.031 625 is 0.664. Then argon 0.0075 divided by 0.03125 3165 0.23. Okay. I hope when you add, you get one. Okay. So if you're now let's find out whether whatever approach you said through that it is coming or not. Did you check? Did you check your calculation?
Yes, sir. Yes, sir. I'm getting the same
But-
only. But anyway, I don't know whether the approach is correct or not, sir. For this kind of problem, we can take that mass of the mixture as 1 kg, sir. That is allowed.
That is allowed when? As I said, when it is mass basis.
Mass basis.
Yeah. If volume basis, then it won't be allowed. You have to go the way that you have tried.
Okay, fine, sir.
So let us start like by calculating what is the mass
Mass.
of air. We calculate by that. But the problem is that in that approach, we don't have R value.
R values.
Okay. So R value you have to calculate. You have to calculate R. Yes. For that also you need the mass. So 0.6. It's anyway like if you take 0.6, then also you have to divide by 28 because it is given in mass. Okay. I think you have done some mistake in your calculation. Just check once. Okay.
Oh, okay, sir.
But this way, I think it is more easier for you.
Yes, sir. Absolutely, sir.
So let's go to the next question. A rigid insulated tank contains 12 kg of oxygen at 200 kilopascal, 280 Kelvin, which is kept separate by a membrane from a 26 kg of carbon dioxide. Okay. First and the foremost things, whenever you see it is in terms of mass is given, no, be very happy because then the calculation will be somewhat simpler or the solution will be shorter. Okay. Then because from mass you can directly calculate moles, but from volume you have to first come back. You have to calculate the mass, how much mass. Then from the mass you have to calculate the volume. Okay. So 12 kg of oxygen at 200 kilopascal to 80 and 200 kilopascal to 80 Kelvin, which is kept separate by a membrane from the 26 kg of carbon dioxide at 400 kilopascal 360 Kelvin. The membrane is now removed, allowing the gases to mix and attain a final uniform state. Okay, final uniform state. Both the gases are considered to be ideal, another keyword. Then the final temperature of the mixture is. I'm giving you, I think you need 5 minutes for this. Take 5 minutes and calculate this. Okay. Did you solve?
Yes, sir. I'm trying. I'm getting temperature around 334.4 Kelvin, sir.
Okay. We'll see. What was your approach?
Yes, sir. Here, the rigid insulated tank, here, that heat transfer is 0. So now here, that Q equal to W plus del U. Here, del U change in internal energy is 0. See, the internal energy before mixing, that is equal to after mixing. So here, 12 kg of oxygen, it is mixed with 26 kg of carbon dioxide. Here, the temperature of the oxygen is 280. The carbon dioxide is 360 Kelvin. After equilibrium, definitely the temperature should be lies between these two. Now, that new temperature is what after mixing temperature I have taken as Tm. Now, the heat lost by the one fluid is it is added with the heat gained into the another one medium. So I have equated and then obtained that temperature values. It is around 334. I don't know whether approach is correct.
And where did you get the values of CB and CA?
Yes, sir. I have referred to the table, sir. Essential in Bold's book. So
Okay.
table I have referred for oxygen as well as carbon dioxide. That CP value CO2 is for 0.657 and 0.658 is oxygen for oxygen.
Okay. Yeah. Seems like your approach is perfectly right. We'll see the answer. The approach is perfectly correct. Okay. So let's see. So first of all, whenever such question comes about the final temperature, and so first and foremost thing that you should do is you have to do the conservation of energy. And can you do this? Like first. So that's the first thing you should know from such type of question. Then the second thing that you will know is rigid insulated tank. So what does rigid insulated tank mean? Rigid means the volume cannot change. So delta V is equal to 0. That means there won't be any boundary change, that won't be any work due to the change in the boundary due to the displacement of the boundary. So work done is 0. Then the second thing is the insulated. That means Q heat transfer is 0. Okay, is equal to 0. And from the question also you get to know there is no external energy or external work done is transferred. Okay, so you finally get that delta U is equal to 0, or U summation of U before mixing is equal to U after mixing. That's all. This is the concept that you require for solving this question. So when it is before mixing, you will be having separate UO2 plus separate UCO2. But after mixing, that will be a mixture of CO2 plus O2. Okay. So what do you want for the other thing that is to be treated as ideal gas. And when you treat ideal gas, what is the formula for U, the internal energy? It is mCV T. Let us denote 1 as before mixing. 2 is after mixing. This is the state points. Okay. Okay. mCV T1 O2, M also O2, CO2 O2 plus M CO2 CV CO2 plus T1 O2 CO2 is equal to M CO2 plus MO2 CV of the mixture the final temperature T2. Okay. Then the thing that you have to find out, what is the CV value for oxygen. So see, as we have already said that this specific it is mostly dependent on the temperature, and this is for ideal gas. So only you have to see the ideal gas. You don't have to take into consideration of the pressure changes. Okay. So the refer to table number in Cengel and Bowles. Refer to table. I would just tell you. Table number A2. Table A2. Okay, of Cengel and Bowles. So table A2, if you see, okay, so table O2 tells you the relationship, but the perfect value you get in table, yeah, table A2, page number 899, as I can see. So for oxygen, you get CVS 0.658. Oxygen is 0.658 kilojoule per kg Kelvin, and CB of CO2 is how much? Carbon dioxide is 0.657. 0.657, almost same. And just cancel it, but better to go step by step. So what will be the CV of the mixture? It will be the mass average of both of them. So just multiply. So oxygen is 12. So 12 into 0.657 plus 26 into 0.657 divided by 12 plus 26. Find out what is the CV of the mixture. Is 12 into 0.657 plus 26 into 0. Sorry, it was 68, 0.658. So 12 into 0.658 plus 26 into 0.657 divided by 12 plus 26 is 38. I'm getting 0.6573. 0.6573. Now calculate. Now put all of this. So first is 12 into 0.658 into what is the temperature? Take it in Kelvin, 280 plus 26 into 0.657 into what is the temperature is 360 is equal to 38 into 0.6573, 0.6573 into T2. T2 we have to find out. What is T2? Find out from this. 12 into 0.658 into 280 plus 26 into 0.657 into 360 divided by 38 divided by 0.6573. You're getting T2 as 334.7 Kelvin. Okay, you got 0.4. I think it's fine. Okay, so the correct answer is 334.7 Kelvin, and I hope you understood this question. Okay.
Yes.
Now moving to question number 9. A rigid insulated tank contains 12 kg of oxygen at 200 kilopascal and 280 Kelvin, which is kept separate from a. Okay, I think this question is. I think this question is repeated. Okay, so for this, you try to find out. Try to find out what is the enthalpy. If I have just written this question, try to find out what is the enthalpy. What is enthalpy at each of this temperature? Gases and mixtures. Find out. I'm giving you 5 minutes, calculate. Very simple, same as above. As it is idle, just you have to do CPT T. So find out.
Sir, that C here enthalpy of the mixture after mixing mass of the mixture into Cp of the mixture into T2. Whether it is correct, sir?
Yeah, correct.
Yes, sir. Cp value of oxygen 0.918 kilojoule per kilogram Kelvin.
Yeah.
Cp of carbon dioxide 0.846 kilojoule per kilogram Kelvin. Cp of oxygen 0.918 and the Cp of CO2 0.846 kilojoule per kilogram Kelvin. And then the Cp of the mixture, it is 0.869 kilojoule per kilogram Kelvin. In the previous case, we have calculated the temperature, final temperature, that is
Correct.
334.7 Kelvin, 334.7 Kelvin. Now mass of the mixture is 38 kg. So M, Cp, and then T2 is around 11049.
Okay. So perfectly right. So you have CP values from the table. This you get from the table A2 of Senzel and Bowles. And after getting all these values, CP mixture you can calculate by doing the mass average. MA CPA plus MB CPB by MA plus MB. Now once you do both of them, you get 0.869 and you have mass of the mixture as 38. So let's calculate what is delta HA. So not delta HA, HCO2 1. So it is 0.918 into 12 into what is the temperature? It's 280, 3084. kilojoule. What is CO2 enthalpy? H of the mixture. $38 into 334.7, which is 11052.46. I hope this is what you got.
Yes, sir. I got 11049, sir. Anyway,
Okay.
the answer is 11052. You are getting, yes, sir.
Okay. So this is all about question number 9. Let's go to question number 10. A mixture of 0.5 kg of nitrogen, 0.5 kg of oxygen is kept inside a piston cylinder arrangement at 100 kilopascal and 300 Kelvin. Now 800 kilojoule of heat is added at constant pressure. If both nitrogen and oxygen can be assumed to be a perfect gases with Cp value is given here 0.922 and 1.042 kilojoule per kg Kelvin, then the increase in the entropy of the mixture. You have to find out. I'm giving you, let's say, 5 minutes to solve this question. Are you solving?
Yes, sir. Yes, sir. Yes, sir. Approach is here. Del S increase in entropy. Heat is added into the system. Entropy increases. Here, that is around. For finding this, it is a constant process. Constant pressure process is following. That's why mass of the mixture into Cp of the mixture into ln of T2 by T1. That is the final formula I have used, sir. For this, here the amount of heat added into the system is also given. So from this, I try to calculate the final temperature T2. After finding the T2, I applied the T2 in the del S formula, sir. So answer is around 1.29 kilojoule per Kelvin I have obtained, sir. I would like to verify it.
Okay, what is T2 you got?
It is around 1120 something, 28 something.
1000?
128.
20.
Right.
Okay. First and the foremost thing that it has said is piston cylinder arrangement, and it has a constant pressure process. And the it is said that heat is added. Has not said anything about the work done. So that means that when heat will be provided to keep the pressure constant, it will rise up because there will be expansion as well. Okay. So in this 0.5 kg nitrogen is there and 0.5 kg O2 oxygen. So here the basic formula that you have to find out what is T2. And as he said, so delta S that you will get Cp ln T2 by T1. And talking about specific entropy. So H1 plus Q is equal to H2. Okay. So first of all, we need to find out what is H1. H1 means summation of an enthalpy of both nitrogen and oxygen. One kg into what is the Cp of the mixture? Nitrogen Cp is 1.03. Oh, sorry, it is given.
Point 982, sir.
It will be 1.0.923 divided by 2 because as the mass is same, so it is 1.042, 1.042 plus 0.922 is divided by 2 is 0.982. Okay. One into 0.982 to T1 is kept in the 300 Kelvin. 300 Kelvin plus 800 joule is added, kilojoule is added. So our value is in okay. So here 0.982 to 1 into T2 300 plus 800 divided by 0.982. I think here you have done some mistake. T2 I'm getting 11114.66. Just calculate once again.
Yes, sir. Correct only, sir. 1114.66. Yes, sir. Correct, sir.
So
This is the correct.
once T2 is done, calculate delta S for O2. So 0.922, or you can calculate together also, not a problem. So CP 0.5 ln 100 1114.66 divided by 300. So 0.5 into 0.922 into 66 0.60 0.605 delta S of kilojoule per kg, not kg, kilojoule per Kelvin. S of N2 on 0.42 4.66 1.36 kilojoule per Kelvin. So delta X mixture plus 0.605 is 1.972. 1.972. I think just for your temperature issues only, the answer is different, but the approach is perfectly right. So the correct answer is 1.972. Okay.
Okay, sir.
Now going to the next question. I think this is also the same question as earlier. Okay. Just this is a question for you. A mixture of 0.4 kg of helium and 0.6 kg of argon is contained in a piston cylinder arrangement of 120 kilopascal and 290 Kelvin. Now 500 kilojoule of heat is added at a constant pressure. Both helium and argon can be assumed to behave as ideal gas at with specific heat values at constant pressure of this much and this much. Now you have to find out, calculate temperature, final temperature, of course, final temperature, and then entropy change of the mixture. Find out. I'm giving you for this. I think you don't need much time. Giving you 3 minutes. Calculate it.
whether the temperature is 499 Kelvin, sir, after release.
What is the entropy?
Doing, sir. One point 1.296 kilojoule.
Okay,
per
we'll
Kelvin.
see. Okay, so first of all, you need to find out the final temperature. And how do you find out the final temperature? As I already said, to do the energy conservation. So the mixtures, what is the mixture CP? CP mixture 0.4 into 5.193 plus 0.6 into 0.520 divided by 1. So 0.4 into 5.13 or 193 plus 0.6 into 0.5. This is 2.38. 3892 kilojoule per kg Kelvin. So you calculate 2.3892 CP, and when it is a mixture, it is 1. So the temperature is 290 plus 500 kilojoule is added, equal to 2.3892 into T2. So from here, T2 that you get is 2.392 to 290 plus 500 divided by 2.3892 is 499.2. 499.27 Kelvin. Okay, I think that is correct. So then delta S mixture. There we calculated for each species. You can directly write 2.3892 to C1 is CP ln 499.27 divided by 290. So 499 divided by 290 ln into 2.38. You get 1.297 kilojoule per kg. Kilojoule per Kelvin. Okay. I hope such questions, if you comes again, you can solve it. I think these are more than enough for you to understand the to calculate how this question can be solved when the mixture of gases are involved, and if they are non-reactive, obviously. Till now we have only covered that much only where the gases are unreactive, and I think we have covered almost all types of questions with this. And I hope it will be clear to you. Okay, so that's all for today.
Okay.
If you have any doubt, you can write a mail, and I will be if I will get some time, I'll surely answer it within a day. Okay.
Okay. Thank you, sir.
Okay.
I hope so. The solution for the problem will be released soon, sir, for assignments. For last
But
week
most
assignment. Yes.
but most of the solutions. Okay, solutions. I think yeah, it will be released.
Oh, fine, sir. Thank you, sir.